Alright, next we're going to look at some proofs for NP completeness, and our first example is going to be the formula satisfiability problem, also known as SAT. Okay, so an instance of SAT, the formula satisfiability problem, is just any Boolean formula, we'll call it phi. It's composed of n Boolean variables, we'll just label them x1 through xn, and then a number of Boolean connectives. Okay, and so these Boolean connectives, they can be and or not, as well as implication and biconditional. Okay, so this is a little more general than what we saw in circuit satisfiability, where we just allowed and or and not. So this formula satisfiability also allows implication and biconditional. Okay, so that's the implication and biconditional in addition to and or and not. Okay, and of course also parentheses. Okay, and so formula satisfiability is very similar to circuit satisfiability. The decision problem is, can you find some assignment of truth values to your variables so that the formula evaluates to 1. Okay. So we can encode any Boolean formula in a length that's polynomial in the number of variables plus the number of connectives or gates that we have. Okay. And so that is what we need to show that this problem, SAT, is NP complete. Okay, so in terms of our methodology for proving that something is NP complete, the way that we're going to do it, okay, for every problem is we are trying, first of all, we have to show that what we're trying to prove is NP complete is in NP, that it can be verified in polynomial time. And the second thing we have to do is show that it's NP hard. Okay, so how do we show that something's NP hard? Well, we select a known NP complete language. Okay, and then we describe some algorithm that computes a function that maps every instance of that known language to an instance of the one that we're trying to prove is NP complete or NP hard. Okay, and then after we describe that algorithm, we need to show that that algorithm that we used to map the known problem to the one that we're thinking about, that it satisfies the fact that for every string, if it's in the known language, then what we map it to, the instance that we map it to, will be in the language that we're thinking about. Okay, and of course we have to also show that whatever mapping or function that maps one instance to the other runs in polynomial time. So this is going to be the outline of our proof for all of the problems that we consider. Okay, so now that we've seen that outline, we're going to look at the proof that formula satisfiability, or SAT, is NP complete. So first we need to show, step 1, that the problem is in NP. So is formula satisfiability in NP? Can we verify satisfiability in polynomial time? Okay, well, if we were given a solution, okay, to the formula, we could just take our formula and replace every variable with a value specified in the certificate and then just evaluate it. Okay, so we do that substitution, we do the evaluation, that's all going to be done easily in polynomial time. Okay, so the substitution basically takes it's going to be whatever the size of the input is, and the evaluation is also, so it's just going to be some constant times the length of the input. Okay, so next we need to show that it's NP hard, and so we need to pick a problem that we know is already in NP and show that we can find a polynomial reduction to formula satisfiability, the one that we're thinking about. Well, so far, the only problem that we know that's already NP complete is circuit satisfiability. So that's really our only candidate right now. We have to pick a known NP complete problem and then polynomially reduce it to the problem that we're thinking about. Okay, so that's what we need to do. Now, we might think that we can just go and replace every gate with a formula that represents that gate, and then substitute that expression into another expression for the next gate, and then just kind of do this inductively and grow the formula. Well, the problem with this is we can end up getting exponential in the size of the input if we keep substituting the formula into another formula, substituting that into another formula, substituting that into another formula. That can grow exponentially. So that, even though it seems like the intuitive way that you would do it, we can't guarantee that that is polynomial in the input size. So there's a different algorithm that we need to use to do the mapping from circuit satisfiability to just formula satisfiability. Okay. So what we're going to do is go to every wire. So we're going to label every wire in the circuit. Okay. And then we're going to create a formula that has a variable that's associated with that wire. And when we look at the expressions that get generated for our formula, okay, so we're going from a circuit to a formula. So we're going to express how each gate operates. Okay. And so the way that we're going to express that is we're going to look at the output wire, and that output if and only if, and then an expression that uses the logical function of the gate. So let me kind of show you what that kind of looks like. So for example, okay, these expressions right here are all of that form. So if I look at this one, x4, if and only if, not x3, represents this gate right here. Okay, so the output right here, okay, should be exactly the same as the function of this gate, which is to negate x3. Okay, so the output of the NOT gate will be essentially, you know, this will be a 0 if this is 0, and this will be 1 if this is 1. They have the same operation, x4 if and only if, not x3. So this is specifying the correct functionality of how this gate works. Okay, here's a wire right here, x5. Okay, so that's the output of this OR gate. Okay, so x5 is equivalent to the OR of x1 and x2. So x5 if and only if x1 or x2. So this is expressing, okay, how this gate works. So hopefully you can see that every single one of these, x6 if and only if, not x4, notice that's the input is coming from x4. x7, that's this wire right here, the output of this AND gate. So x7 is equivalent to, or if and only if, and it ANDs together. x1 comes in as an input, x4 comes in as an input, and x2 comes in as an input. So x1, x2, and x4 are being ANDed together. x8, if and only if, x5 and 6 are ORed together. So the functionality, so the value on x8 is equivalent to the OR of x5 and x6. Okay, x9 is the OR gate, x10 is the AND gate. Okay, so these over here are all just expressing the functionality of each individual gate. Okay, so each of those is a clause, and then the final formula is the AND of all of those clauses as well as the output of the circuit. Okay, so here is the output, x10, and then we AND that with all the clauses that represent each of the gates here. So if you think about what this is doing, this is saying, all right, so the only way for the this formula, the formula for phi, to evaluate to true is if every single one of these evaluates to true. That's the way AND works, right? So that says that the output of the circuit has to be true, okay, and each gate has to have a function that it operates as it's designed to. Okay, so we're only gonna get where the output of this is equivalent to what the gate is supposed to do, which is to negate x3. The output of 5 is equivalent to ORing x1 and 2. So every gate does exactly what it's supposed to do, and the output is a 1. Okay, so that's the only way that you're going to get a 1 for the formula. Okay, so thinking about that reduction, okay, we have to show, so we've selected our known NP-complete problem, we've described an algorithm that maps it, and now we need to show that the instance that we've mapped to, okay, so we have a formula and we have now a circuit. We have to show that the circuit is 1 if and only if the formula is 1. Okay. So let's say that the circuit has a satisfying assignment. So the circuit can have an output of 1. Okay, so if the circuit has a satisfying assignment, well, then each wire of the circuit has a well-defined value. Okay, and if there's a well-defined value, the output of the circuit has to be 1. So if it has a well-defined value, that means that all of the gates are doing the job that they're supposed to. Okay, so these will all be 1, and the output, because it's satisfiable, the output is also going to be 1. So the output of the circuit will be 1, and then so if it's satisfiable, then the formula will be 1. And then if we go the other direction, if some assignment causes it to evaluate to 1, then the circuit would be satisfiable. So we're going the other direction. So the first one was, hey, the circuit is 1, then the formula has to be 1. What about the other direction? This is an if and only if. So the other direction is, let's say the formula was satisfiable. What would that mean for the circuit? Well, if the formula was satisfiable, okay, then I could just take the values here that satisfied it. I know that this would have to be a 1 if it was satisfiable. That output would be a 1. Okay, and I know all the gates. I would just assign all the values to whatever caused these things to evaluate to true. I would put them all in there, and each gate would be doing its job. The output would be 1, and so the circuit would also be satisfiable. Okay, so it goes both directions. The circuit, if I have a circuit that's satisfiable, it'll make the formula satisfiable. If I have a formula that's satisfiable, it'll make the circuit satisfiable. Okay, and so we have that the circuit SAT is polynomially time reducible to SAT, and that would complete our proof for the NP completeness of SAT.